Okay, so this is from 2018. So we have a conducting loop that's entering this region of magnetic field with a constant velocity to the right. And the magnetic field is uniform and directed into the page. So what they want us to do is, in a coherent paragraph length response, we're going to compare the magnitude and direction of the current at times T1, T2, and T3. So these are the times T1, T2, and T3, and then include an explanation of why there is or is not a current and the direction of the current if one is present. Okay, so there's a lot to talk about there. Okay, so first let's just talk about the background here. So this is an induction question where we have electricity, we have current being generated in a loop with no battery present. So you're looking at this loop, there's absolutely no battery in there, but current can be generated through a change of magnetic flux. So I guess let's just review. So the equation for magnetic flux. So magnetic flux has this funky symbol. This is magnetic flux, and it's equal to BA cosine theta, where B is the magnetic field inside the loop. So when we talk about magnetic flux, we're focusing inside the loop. So B is the field. A is the area, you know, what is the size of the loop exposed to the field, right? So like, I guess here, the area you would be concerned with is the area exposed. So it'd be like that part right there. What's the area exposed to the magnetic field? And then here, there's more area exposed to the field. And then cosine theta, this is the trickiest part. Theta is the angle between the normal line to the loop and the field. It's the angle between the normal line to the loop and the field. So for this loop, the normal line is shooting straight out of the page into your face. And then the field is parallel to that. So the angle here for this problem is going to be 0, and cosine of 0 is 1. Okay, so that's flux. Now, flux becomes interesting when it changes. So we get an induced voltage. So E represents voltage, and it's the same E. So we like, you know, Ohm's law, E equals IR. Voltage causes current. So induced voltage is going to equal change in magnetic flux over the time that the flux changes. So the quicker flux changes, the greater the induced voltage. And this, of course, is going to be equal to IR, right? So induced voltage, which is equal to IR, that's Ohm's law, it can be calculated from taking the change of magnetic flux and divided by time. But we really don't even need calculations for this problem. For this problem is more of like a conceptual understanding. So the thing to realize here, as this loop enters the region of magnetic field, there is going to be a change in magnetic flux inside the loop. And the reason for that is more of the loop, as the loop enters the field, more and more of the loop becomes exposed to the field. You know, so like from this picture to this picture, you know, here we have 1x for magnetic field. Here we have 2x. More magnetic field is present in the loop, so that qualifies as a change of magnetic flux. Now here, at time T3, the flux is no longer changing, because if you look at the flux equation, you know, the magnetic field is constant, and the area exposed to the field, the area of the loop exposed to the field, is no longer changing. So here, the change in magnetic flux is 0. Nothing is changing. And if there's no change in flux, that means that the induced voltage will be 0. And if the induced voltage is 0, the current will be 0. So that's part of the answer. At time t3, the current in the loop is 0 because there's no induced voltage. And the reason why there's no induced voltage is because there's no change of flux inside the loop. Now, comparing time t1 and time t2, the change of flux is going to be equal. And the reason why is the loop is entering the field at a constant velocity. So the change in flux is going to be constant because the new area of the loop exposed to the field, the area of the loop exposed to the field is increasing at a constant rate. So that's pretty much the answer to A. So let's just go through. So, oh, we didn't talk about direction yet. Okay, the direction of the current. Now, to figure out the direction of the current, I'm going to explain it 2 different ways. So the first way is Lenz's law. Okay, so Lenz's law says, in fact, let me write it over here. Lenz's law, this law says that the induced current creates a B field opposite the change of flux. The induced current creates a magnetic field opposite the change of flux. And I want to be clear here. The magnetic field that the induced current is creating, it's not this magnetic field. It's a new magnetic field. All right, so first thing we got to do is figure out which way the flux is changing. So if we look at this loop, so we're figuring out which way the induced current is going to be. So this loop enters the magnetic field. The flux is changing into the page. So the change of flux is going to be in to the page. And the reason why is we go from having a little bit of field directed in to more field directed in. If you go from less field directed in to more field directed in, that's going to be an inward change. So the flux is changing into the page. So what does Lenz's law say about that? Lenz's law says, oh, well, if the flux changes into the page, the induced current will create a new magnetic field that is out of the page. So here's where you have to use right-hand rule number 2. So right-hand rule number 2 is where your 4 fingers curl in the direction of the magnetic field around a wire, and then your thumb is the current. So it's hard to show just on a computer screen, but like put yourself right here, right here on the bottom part of the loop. The induced current is going to make a magnetic field that's out of the page. So we want our 4 fingers inside this loop here. We want our 4 fingers curling outward, which means our thumb of our right hand is going to be pointing to the right, which means the induced current is going to be going counterclockwise. So induced current using Lenz's law will be counterclockwise. Now there's a second way you could figure out the direction of the induced current. The second way to do it is just to use right-hand rule number 1. So using right-hand rule number 1, if you put yourself at the front of this bar right here, so focus on a positive charge, in this rod right here. So using right-hand rule number 1, your 4 fingers are pointing into the page because that's the direction of the magnetic field. Your thumb is going to be pointing to the right because that's the direction of charge motion. And then your palm should be facing upward. So using right-hand rule number 1, the direction of force on a positive charge would be upward, right? A positive charge would be forced upward according to right-hand rule number 1, which is going to lead to that counterclockwise current. Okay, let's go to the next part. Okay, so the loop is removed. So the loop is removed and a proton is traveling to the right in the plane of the page as shown. It enters a region of magnetic field with a velocity of that 3 × 10⁵. The magnitude of the field is 0.03 Tesla. Effects of gravity are negligible. So calculate the magnitude of the force on the proton as it enters the field. This is super easy. So the equation for force of a magnetic field is QVB sine theta. And again, so theta here is, it's the angle. So this theta is defined as it's the angle between, theta equals the angle, it's between the velocity of the charge and the B field, which is going to be 90 here, right? Because velocity is directed in positive X. The magnetic field is in the Z direction. They are perpendicular. So this is going to be sine of 90, and sine of 90 just goes to 1. So force magnetic, we're going to go charge of proton, 1.6 × 10⁻⁹. The velocity is 3 × 10⁵. And then magnetic field is 0.03 Tesla. So this comes out as 1.4. Force magnetic is 1.4 × 10⁻⁵ newtons. Okay, next question. On the figure below, sketch a possible path of the proton as it travels through the magnetic field. Clearly label the path P1. So the idea here is, look, when a positive charge hits this region of magnetic field, the velocity is to the right, and using right-hand rule number 1, so right-hand rule number 1, your thumb is the velocity, your 4 fingers are the magnetic field, your palm is facing up the page, which is the direction of the force. Now what that's going to cause, it's going to cause the positive charge to curve upward. So now let's look at the positive charge right here. So now the velocity is that way. So that's velocity. Force is going to be perpendicular to that. What we have here is the force of the magnetic field always pointing towards the towards the center of a circular path, right? When a charge travels perpendicular to a magnetic field, which is exactly what we have here, a charge traveling perpendicular to the field, the resulting path is circular. Okay, so this proton's going to come in, and what you want to do is you want to sketch a circular path, right? Make it, you know, it's a semicircle. It's from a circle right there, and we're going to label that path P1. Okay, a second proton now enters the magnetic field at the same point from the same direction, but at a greater speed than the first proton. On the figure above, draw the path of the second proton. Okay, so I want to show you the equation here. So the equations go like this. So if we focus on this proton, so proton comes in, let's sum the forces on that proton. The only force on the proton is the force of the magnetic field, which equals MA. Okay, force of magnetic field is QVB. We can ignore the sine theta because that goes to 1. And then this equals M. Now, it's a circular path. It's a circular path. So therefore, the acceleration is centripetal. So we can plug in for centripetal. That's going to be v²/r. So we get this nice equation where one of the velocities cancels. And let's solve this for r. So r is going to equal mv/qb. And The answer to this question lies in this derived equation. So what they're setting up for us here is a second proton. So the mass is constant. It's still a proton. Mass did not change. Charge did not change. The field did not change. So all of this stayed constant. The only thing that changed was the velocity. If the velocity is bigger, the radius must be bigger. So we got to draw a path with a larger, a circular path with a larger radius. So let's make a bigger circle. So I don't know, something like that maybe. It's a larger circle. So that's going to be P2. Okay, last question. So now we have an electric field. So we have an electric field is applied in the same region as the magnetic field so that there is no net force, meaning the force on the proton, is, the total force on the proton is going to be 0. So calculate the magnitude and direction of the electric field. All right, so let's look at the proton when it's in this region here. So it comes in, the force of the magnetic field, using right-hand rule number 1, the force of the magnetic field is up. FB points up from right-hand rule number 1. So in order for there to be no net force, there has to be an equal force down, which would be the force of the electric field. That's what they're talking about here. We have an electric field. So force of magnetic field is up. In order for there to be no net force, the force of the electric field must be down. Now, how could we get a downward force of electric field? Well, the way this would happen, so I'm going to draw plates in here, right? If we imagine plates creating this electric field, in order for the force of the electric field to be down, the top plate would be positive and the bottom plate would be negative. So this is like, you know, we're bringing in another concept here. If you had positive plate, negative plate, remember the direction of the electric field is the direction of force on a little positive charge. So you put a little positive charge between these plates and you're like, which way would the force be on that positive charge? Boom, the force would be down. And that's the force of the electric field. And we define the direction of the electric field to be in the direction of force on that positive charge. So the electric field is going to be pointing down like this, right? The electric field is pointing like that. So we've answered the direction of the electric field. Calculate, indicate the direction. So the direction of the electric field is going to be downward, or actually you want to say negative y. See right here? You want to say negative y. Now, how do we calculate the magnitude? So to calculate the magnitude, so the equation for force of a magnetic field is QVB. The equation for force of electric field is QE. So when we first learned this, I made a big deal. Remember, I related this to gravity. I was like, hey, dude, what's the equation for force of gravity? mg. What's the equation for force of electric field? The m becomes q, the g becomes e. The force of an electric field is QE. So the answer to this question is these two forces must cancel. So we're going to go QVB equals QE. The Q's cancel. The electric field is V times B. Okay,